All right, our last speaker for the session is Christopher Malhas from the University of Texas at Austin.
Just for this one or no? Test. Hello, everybody. My name is Christopher Malhas, and I am an undergrad or recent graduate from the University of Texas at Austin. Thank you. And today I'll be talking about my project, which works with the outflows, as you might have noticed a trend from the past three talks, using the Cosmic Origins Spectrograph on board the Hubble Space Telescope. In particular, we're looking at some of the lowest mass galaxies ever observed. And I worked with my advisor and primary collaborator, John Chisholm, to observe these galaxies and quantify their outflow properties. So while this video plays, I'll sort of briefly give you an introduction into what these outflows are and what creates them. Basically, within the pockets of star formation of the galaxy, you have young, massive stars that are injecting a lot of energy and momentum into the surrounding gas, and that creates the observed outflow. But it also serves to regulate the gas content as well as the metallicity of the galaxy. And in particular for low mass galaxies, this might be a little bit pixelated, but you can see the outflow, the gas outflowing from the galaxy. And this is particularly effective at regulating the gas content of low mass galaxies because they have a lower gravitational potential. And so that has huge implications for how much of the mass of a galaxy is ejected. And then from this plot on the right, we have this mass loading factor along the y-axis. And that is basically a stand-in for the ratio of how much mass is lost to how much new star formation is going on. So as you go to lower and lower masses, as you go to the left of the plot, you're actually losing more proportionally more of your gas due to these outflows. So this project aims to quantify how the low mass relationships in terms of velocity and equivalent width scale in terms of host galaxy mass. So in red, we have here a sample of galaxies that was studied by John Chisholm in 2016. And from here on out, I'll just refer to these as the massive galaxies. And in blue, we have my sample of in the blue dots, we have my sample of really low mass galaxies at mass ranges that have yet to be studied. We have John has two really low mass galaxies, but he was unable to determine many of the outflow parameters that we're interested in because we needed more sensitivity that the Cosmic Origins Spectrograph affords us. So let's talk about how we actually go from the spectra to these outflow parameters like velocity. First, we undergo a Starburst 99 fitting model to the spectra, but that doesn't get us quite all the way because, for instance, we know that the silicon 3-1206 line wouldn't be absorbing photons way out to these velocities and these wavelengths. So we do a little bit more of spline fitting, and I wrote extensive code to spline fit the spectra in order to give us these much more nicely constrained continuum levels. From these continuum levels, we're able to quantify a few parameters. I'll focus one on the V90, which is basically where the profile reaches 90% of the continuum absorbed. That's where we can safely say that there is gas outflowing from the galaxy at this velocity. And then we also quantify the equivalent width, which is basically a stand-in for how much gas you have in that particular transition. We look at a variety of different ionization states, and the oxygen 1 transition is our lowest ionization line, and the silicon 4 represents the highest ionization feature that we study. These all demonstrate the silicon 4 for 6 galaxies, and they go from low mass to high mass. So actually at the top is some of our galaxies, which have a mass of a stellar mass of 10 to the 7 solar masses. And then as we get to the bottom, you can see in the bottom right, NGC 6090 is actually a 10 to the 10 solar mass galaxy that was studied previously. And as you can see, it produces much higher velocities for their outflows. So what sort of relationships do we actually observe? First, let's look at velocity. This represents the mass of the galaxies plotted alongside their velocity. And what we can see is that all our results end up within 1 to 2 error bars of the predicted trends. In black, you have the trend from just the massive galaxies, and then the dashed blue line represents the new trend we derived with the combination of high mass and low mass galaxies. So the trends for velocity scale rather nicely. This is something we've known. We've thought that this would occur, but the observations for these low mass galaxies have yet to be observed. And now that we have this quantification, we can use this to basically set the initial conditions for simulations and test our simulations and whether or not they drive realistic outflows. And then in terms of equivalent width, one thing that we notice is that as you go from low mass galaxies to high mass galaxies, the lower mass galaxies are actually more highly ionized. So this produces a divergence in the trends where the highest ionization trend, silicon-4, is actually underpredicted by the trend from just the massive galaxies, and the lowest ionization parameter, oxygen-1, is overpredicted. And so what we can use these parameters to also benchmark our simulations, and this gives us interesting results because now we're able to actually quantifiably say how much more gas is in a particular ionization state of the outflow for galaxies at the lowest mass ranges. And so that is all. I'll just leave these conclusion slides up for you. And if you have any questions, I'll be more than happy to answer them.
Do we have any questions?
Real quick question. I just wanted to know how far away these galaxies were.
They are incredibly low redshift. Most of them are about a redshift of 0.015 to 0.017. We actually have a really hard time, and maybe I could show this clear. In the light blue is like the error bars, and the galaxy in the middle left is IC 2779, and that is the furthest galaxy. And so as you can see, as we get to further, like marginally further redshifts, the confidence with which we're able to say there's gas being absorbed here goes down significantly. So thanks to COS, we're able to make these observations in the really, really local universe, but it'd be amazing to observe similar sized galaxies at further and further redshifts.
Thank you. Hello, great talk. You kind of alluded to the fact that silicon-4 is more prominent in low mass galaxies, correct? Right?
Yes. So we have about like 70. We're able to confidently say about 74% exists in the silicon-3 transition. And then from there, it's just like where the other like 30 or so % is allocated, whether it's in the higher mass or in the higher ionization or lower ionization states. So for just the low mass, yes, we think that there's the larger equivalent widths for silicon-4 indicate that there's more gas in that particular transition.
Do you have any idea why that is specifically for low mass, or any ideas?
We have talked about it extensively. The data, we would need a more robust data set in order to say reliably why. Part of it is due to the metallicity. So as you drive more metals out of the galaxy and lose them because you don't have enough gravitational potential, you're going to have more inefficient star formation, and that contributes to the ionization state. John's talked about a lot of very intricate science that we'd hope to do that we just don't have the data for yet.
Have you ever considered creating a mass fraction to like illustrate this?
We can't. We derive column density, so yeah, we could do the mass fraction. The interesting parameter we're mostly hoping to publish with just this data though is those like velocity rates, because that's one, very relevant to simulations. I kind of want to go to grad school hopefully for simulations, but I'm fine with observations as well. So we want to quantify those results, but also it's highly relevant to his paper and other papers in the literature.
Thank you. Thank you.
So just a very simple question. So how significant is this slope difference?
So actually this morning, I took the sigma relations and the significance out of these plots because we thought it might be too complicated to get into, but I'm glad you asked. So for the oxygen transition, it's the weakest absorber. So that is our weakest significance relation. It has a sigma value of about like 3.4. But for the silicon-4 lines, we're actually pretty confident in those. We have significance upwards of 5, which we're very proud of. But it only comes with the fact that the silicon-4 has less error associated with it because it's a stronger transition.
Okay, thank you.
Could you comment on the mass outflow rates of these objects?
So I haven't actually derived the specific mass outflow rates. Like I mentioned, we have column density calculations. So in theory, a follow-up paper or follow-up work could be done on that. But just comparing the equivalent widths would give us a reasonable stand-in for mass outflow rates. But we would imagine that the same trends would exist, like we would imagine that we'd have that similar divergence. But I'd be more than happy to discuss the mass outflow rates at another time with you.
Any final questions from anyone from Slack at all? All right. Thank you, Christopher.
Thank you.
All right, everybody. That's the end of our session. Thank you for joining me. We got done a little bit early. I hope y'all guys enjoy the rest of the convention.